great in energy because it is a radiochemical experiment. You expose your mass for a certain time, 1 month for example, and you integrate it, but we are not able to reconstruct the spectrum because it's not spectroscopy. Okay? It's not events by events. Okay? You integrate it in time and in energy. And this is true also for the gallium experiment, Galax or GNO. GNO, I say nothing about GNO. Galax was, at the beginning, was named Galen, and then it was rebuilt and named Gallium Neutrino Observatory. So Galax and GNO is the same thing. SAGE is the Russian detector. They can detect neutrinos with a very low energy, but as in the case of STEMIs, they integrate in energy and time. So this is not real-time detector, only this one is real-time, but the threshold is quite high. So the Borexino detector was constructed in order to see in real time what's happened at starting from a very low threshold, about 200 kV. Okay? And in order to do that, we have to look not to the cherry comply, as in the case of Kamiokande or Sudbury, but we have to employ scintillation light. So I can skip. No, okay. So for what concerns the PP cycle, the Borexino goal are, the main goal was the beryllium 7 neutrino in order to test the solid standard model at low energy, to constrain the beryllium 7 in order to, when I say that thanks to gallium experiment you are able to see the very low energy, I said also that you have to integrate. So you don't know how many neutrinos come from PP, how many from beryllium, and so on, because you integrated. So if you made a spectroscopy and you can say how many beryllium 7 neutrino you have, how many boron 8 neutrino you have, and so on, you can't discover how many PP neutrino simply subtracted from the events detected by Galax. You have to subtract the contribution of beryllium 7 thanks to the one obtained by Borexino. This is the claim. Okay? I have to repeat?
Yes.
Okay. So I said the threshold of Galax or SAGE is very, very low. I mean, it's able to see the PP neutrino. PP neutrino at the less model dependent. I mean, if you see how many neutrinos, you can infer how many photons. That is a contribution 1-to-1. While, for example, for these neutrinos, they depend strongly with temperature. That is a parameter that you have to introduce in the standard model. So, you want to count how many PP neutrino you have. But if you look at with a radiochemical experiment, you have all the neutrinos. You can't say how many of these, how many of these. So, if I have spectroscopy with Borexino, I go from here, okay? I can count how many beryllium 7. I'm not able to see PP neutrino because the threshold is too high. But if I know how many beryllium 7 neutrino I count, I can subtract from the events counted by Galax to subtract the beryllium 7 contribution and say how many PP neutrino I have. Okay? And test directly the hypothesis of the solid standard model. Okay? So I can skip this one. We can also see, because of the spectroscopy, the contribution of PP neutrino, the boron 8 neutrino, and maybe the PP neutrino. I see there is a question mark because actually we fixed our threshold at 200 kV, but in the case is lower than that, we are able to see the very last part of the PP. And so say directly by us how many PP neutrino count. Okay. But this is, we hope, but we are not sure. So, I say that in the sun, 98% of the energy, almost 98%, come from PP cycle, but we have also CNO, and up to now, nobody saw neutrino from this reaction. And this is important because maybe I can skip this. Okay, try. There is a possibility to see the metallicity of the sun, and for metallicity I mean the number of elements that has a mass heavier than helium, and you see at the surface of the sun by spectroscopy, simply by spectroscopic means. And in the past they agree very well with heliosystemology, but from 2005 we are faced to this controversy because the last study indicated that metallicity is lower than the one predicted 10 years ago, and this destroys the agreement with heliosystemology. The only way to test, because when you speak about metallicity by spectroscopy, you see what's happened at the surface. By means of neutrino, you are able to infer the metallicity of the total mass of the sun. This is the difference why we wanted to employ neutrino. So, 15 years ago, you have to obtain a flux that is 30% smaller for what concerns CNO. This is, do you remember, nitrogen plus fluorine is the neutrino connected to the CNO cycle. So, if you are able to see the CNO neutrino, okay, it's the first time that somebody are able to see this neutrino, and we can count in order to resolve this controversy. This is another motivation to this experiment. There is, besides neutrino, solar neutrino motivation, other motivation that is about neutrino itself. This is when I wrote here the probability that an electron neutrino become a mu neutrino. Do you remember the formula I wrote here? This one. If you plot this one in this way, okay, you can see here, this is the probability versus energy. You obtain this shape, and this is the measurement by snow, and here is 0.35. You can see this one, probability, the ratio between PCC and PNC gave 0.35, and this is the point, 0.35. And you extrapolate this one, but you don't know actually what's happened here. The only point we have are those inferred by Galex and chlorine that integrate in energy. Okay? So in order to actually prove that this shape is correct, you have to detect in real time. So this is the point, for example, this is Galex or sage, and this is chlorine. You have a big bar, and you can say nothing about the correctness of the shape. Maybe it's this one, maybe it's another one, depending on the model you choose. Okay? I have to say that for what concerns the high energy oscillation is driven by the macro effect that took place coming from the core to the surface of the sun. For what concerns the low energy, the oscillation is driven by vacuum oscillation. It's oscillation from the surface to our planet. Okay? Okay, there are also, we plan also to detect